oxygen transport. How do we did you like that? Oh, actually, some of you may not have taken the exam yet, right?
Nope.
So there's one question I was gonna tease you about.
You can tease us.
So how do we transport oxygen?
Mostly by far on the hemoglobin.
Absolutely, by far on the hemoglobin. So we do it. We carry it bound to hemoglobin. And we carry it dissolved
In plasma.
in plasma. That's really it. That's how we carry oxygen.
Mm-hmm.
Carbon dioxide we carry dissolved as carbamino compounds. How else? There's a
Bicarb.
table in there. As bicarbonate.
And hydrogen bicarbonate. Most of it's bound to hemoglobin.
Yeah. And
Right.
so carbamino compounds, bicarbonate is hydrogen ions. And then bound, we carry it as carbamino compounds as bicarbonate. Why did I do that again?
Bicarb.
C-A-R-B-O-N. And
CO3.
is hydrogen ions. So we carry oxygen bound and dissolved, and we carry carbon dioxide bound and dissolved, but in slightly different means. And the interesting thing about carbon dioxide is that up until now we've been suggesting that when we release oxygen from the hemoglobin, it gets to the tissues take the oxygen off, uses oxygen to create ATP, and then creates carbon dioxide as a byproduct of respiration. We combine that with water, or we hydrate water, CO2 with water, and that forms carbonic acid. Carbonic acid is a weak acid, and that's why we say that CO2 is an acid, or the way we associate acid-base balance is that carbon dioxide is the acid. And the reason why it's an acid is because it always dissociates into hydrogen ions plus bicarbonate. Now what's interesting about that is that hydrogen ions is really where we get the definition for CO2, inverse log.
For pH.
Yeah, inverse log of the hydrogen ions concentration for pH. So sometimes the most difficult aspect of acid-base balance is understanding that if pH is going down, if pH is becoming acidic, that means that the CO2 has to be going up. And there's this inverse relationship to CO2 and acid-base. If acid base goes up and we become alkalotic, that must mean that the CO2 is going down and we're hyperventilating. So we have to make that association, and that's probably the biggest challenge in this whole chapter, is making an association between hydrogen ions and pH. And recognizing there's an inverse relationship, inverse log of hydrogen ion concentration. Well, this is the acid. I mean, the way we describe acids, I mean, a definition aside from the inverse log of the hydrogen ion concentration, that's pH. But the definition of an acid is that it donates, hydrogen ions. So carbonic acid releases its hydrogen ions. That's why that's an acid, is because it dissociates into bicarbonate and hydrogen ions. The hydrogen ions is responsible for the acid. The bicarbonate is, oddly enough, the base in that relationship. And there's an ionic equilibrium too. We've got a positively charged ion and a negatively charged ion in that reaction. So that's the interesting thing. the take-home message then for how we transport CO2 is simply 3 ways in plasma and 3 ways in bound to hemoglobin. What is it the book describes that when we release the oxygen, then it makes the hemoglobin able to carry or to bind carbon dioxide onto the hemoglobin? Carboxyhemoglobin. What's that called? Did you look at anything called, or that was relative to the Haldane effect or the Bohr effect? How do you understand the Haldane effect and the Bohr effect? There's a couple of definitions we should probably be familiar with. Go ahead, Alicia.
It says deoxygenated blood enhances the loading of CO2 is the Haldane.
Haldane. So when oxygen is released in the tissues, and that's the whole function of the blood, is to oxygenate itself in the lungs to send this oxygenated blood out to the tissues. The tissues have to extract the oxygen to create energy. But the very fact that oxygen then moves, and it does so by shifting the curve to the right. Remember that discussion yesterday, last week, is that when we shift the curve to the right, it enhances unloading of oxygen at the tissues. So once the hemoglobin releases its oxygen, the Haldane effect makes it necessarily easier to load carbon dioxide in its place. And so in the tissues, oxygen is being released to create energy. Carbon dioxide loads onto the hemoglobin, and that oxygen then creates ATP and CO2 in respiration. That's really the definition of respiration, is at the cellular level. So when people say that someone has suffered trauma and they're in the ICU on a respirator, is that necessarily true? Do we actually respirate for them? We don't. Respiration is an internal process that happens at the cellular level. Respiration occurs with the unloading of oxygen, creating ATP, and then loading hemoglobin back up with carbon dioxide, as in the Haldane effect. And that Haldane effect then enhances the loading of CO2 back on the hemoglobin. So respiration occurs in the mitochondria at the cellular level. Ventilation is what we do. We move gas from the environment into our lungs so that it can be loaded onto the hemoglobin in the first place. Okay. So how does the Haldane effect relate to the Bohr effect? What's the difference? What does it say? What does it say for the Bohr effect in there? Because certainly there will be a question on the Bohr effect. What do you think? It's similar to how we load. It might be earlier in the chapter there. Just find it. The Bohr effect. The Bohr effect simply says that. Oh, go ahead, dear.
Bohr effect. The effect of PaO2 and pH on the oxyhemoglobin curve is known as the Bohr effect.
Yeah. So the higher the CO2,
266.
the stronger binding it has. So once it's bound to the hemoglobin, it binds fairly tightly. The higher the level, the tighter it binds, basically. So once carbon dioxide is on the hemoglobin molecule, the higher that CO2 is, the tighter it holds on, and it's more of a linear kind of a relationship. Oxygen, as we know now, is a sigmoid relationship. You know, there's a flat portion of the curve and a steep portion of the curve. The CO2 curve is more linear. So the higher the CO2, the tighter it binds. There's not any other way to state that. So the Haldane effect and the Bohr effect. Let's see. So as oxygen is being released in the tissues, we create ATP and CO2. What about when we don't use oxygen? Or maybe we're hypoxic. The oxygen level on the hemoglobin molecule is lower and we become hypoxic. If the tissues don't have enough oxygen, we create less ATP. Maybe, is it 3, Kyle? Remind me. Is it 2 or 3 ATPs?
That was 2.
I think it is 2 also.
That's if it's
Without anaerobic respiration.
yeah.
2 ATPs and lactic acid. Okay, so lactic acid is when your tissues build up. I mean, you're not aerobically getting enough oxygen to your tissues, and your tissues create lactic acid. That's the stiffness and soreness you get after you exercise without breathing enough to get your tissues with enough oxygen. When I go out and try to run a mile, I just get on my bike now. But when I used to try to run a mile, after the next morning when you wake up stiff and sore, that's lactic acid. So the stiffness and soreness is because the tissues didn't have enough oxygen to do the work that it needed to do. So it created energy to a smaller degree and then created lactic acid. Well, on a blood gas, there's a way to measure lactic acid. We actually get a number for lactic acidosis. And aside from our blood gas, we'll get pH, CO2, PO2, bicarb, saturation, content, carboxyhemoglobin, methemoglobin, base excess, and lactic acid. So what's a normal lactic acid level on an ABG? Have you noticed in clinical? Near the bottom, they'll probably print out a lactic acid. It should be near 0 or less than 1. So as long as we're aerobically ventilating. But sometimes you'll see a pH that's 7.35 and you'll have a lactic acid of maybe 5. And it just means that the lactic acid is building up. It could be a reason for respiratory failure before respiratory failure happens. So before it's reflected on an ABG with just ventilation and CO2, sometimes you'll get an early indicator of lactic acidosis and diminished ventilation from this lactic acid. So don't disregard all the information on your blood gas.
So lactic acid will increase the pH?
It will decrease the
Oh,
pH.
decrease.
Lactic acid will diminish or decrease the pH below 7.40. So it can be a reason. It could be a red flag is all. So if your ABG says pH of 7.40 and a CO2 of 40, but your lactic acid's 10, that's an indicator. It's a red flag that maybe we're not getting enough oxygen to our tissues. It seems to me like there are always markers that indicate how a patient's doing, and it may not always be the lab test that you expect. In this case, we're always checking blood gases for oxygenation and ventilation. We want to see what the PO2 is. Usually physicians want to see the PO2, and they want to know if the CO2 is normal, 35 to 45, and what if the pH is acidic or alkalotic. Were you going to say something, Alicia?
I was just, I was wondering, like, when you are exercising,
Yeah.
since that's where lactic acid can build up in the muscles,
Yeah.
is there a way to prevent it?
There is. Breathe, you have to breathe. And we do that, don't we? I mean, if I was to run around a mile.
I'm usually breathing, but I'll still get sore.
Yeah, I'm breathing like crazy. So you're trying to increase the ventilation, but it may not carry enough oxygen, or maybe another way would be to take a big hit of oxygen before you started running in the first place. That might be a way to. The guys that are playing football at Mile High Stadium in Denver, they're on the sidelines huffing oxygen.
I see that all the time.
You see that all the
Like your chargers.
Yeah, exactly. So they're at 5,000 feet, their PO2 is in the 50s, their tissues is not as efficient carrying oxygen. They are slightly hypoxemic, but what that does is it slides them down on the steep portion of the curve so their tissues can utilize the oxygen better. But it always helps to have a little bit of oxygen on the side. So that's what you can do to prevent lactic acid. And maybe I wonder if they do it consciously to prevent lactic acidosis, or if they're doing it just because they feel short of breath. I don't know. I would like to know the answer to that question. I don't know. So that takes us away from carbon dioxide transport and more towards acid-base balance. So the relationship of CO2 to acid-base is that CO2 is the acid. CO2 dissociates into, well, it combines with water to form carbonic acid, and carbonic acid dissociates into hydrogen ions and bicarbonate. Okay, so CO2 is indeed the acid. The more CO2, the higher the carbonic acid concentration that dissociates into higher hydrogen ions, and the pH then being expressed as the inverse log of the hydrogen ion concentration. I will definitely ask a question about the definition of pH, and it's the inverse log of hydrogen ion concentration. Well, we can do that by measuring how much carbonic acid there is in the system. So one of the ways that the text tries to bring out how acid-base balance is described, and I want to do this in sequential information. So on page 295, there's a little box down here in that just kind of check that little box, and we'll use it here in just a bit.
What page?
295. So we're going to check that little box at the end. And okay. So when we talk about acid-base balance, acids are substances that donate hydrogen ions. So in this case, if we got hydrogen ions, that would be the classic definition of acid. Acids, and I wanted to use the right example. They use hydrogen and chloride. So one acid is taking a hydrogen ion and combining it with a chloride ion. Well, the hydrogen's positive and the chloride is negative, and that yields HCl, which is hydrochloric acid. Hydrochloric acid is a very strong acid. Okay. It's associated with stomach contents. It's what breaks down our food in our stomach. The stomach is lined with cells that secrete hydrochloric acid. So I said that carbonic acid is a weak acid and hydrochloric acid is a strong acid. Well, your body doesn't really know the difference, but it does have mechanisms to reduce the acidity of the system. And the way that it changes the acidity is by using something called a buffer system. So here's another good definition in this next chapter to try to understand how the body uses acid base in order to balance within a fairly tight range, as it uses a buffer system. So hydrochloric acid is a strong acid. Forgive me, Alicia. Let's see. And so the way it buffers, the way the body buffers these strong acids is they use the sodium bicarbonate. So sodium is NaHCO3. That's the chemical compound for sodium bicarbonate. Sodium bicarbonate, carbonic acid, H2CO3. So sodium bicarbonate, carbonic acid. And so your body has available stores of these two compounds. This is a fairly strong base, and this is a fairly weak acid. Actually, this is a weak base and a weak acid. So in the case of hydrochloric acid, what your body does is it takes this system and it combines it with this strong acid. Okay? So we can take, if this is the acid, the sodium bicarbonate carbonic acid buffer system, and the definition, by the way, of a buffer particularly is that it minimizes the effect of pH. Okay? The buffer system is designed to minimize the overall effect of pH. Your body system works optimally at pHs between 7.35 and 7.45. It's a fairly narrow range, but the way that it's described, the way the pH is described, like we've said, is the inverse log of the hydrogen ion concentration. So hydrogen ions is what we're measuring with pH. We keep that pH fairly small range, 7.35 to 7.45. So if a patient were to all of a sudden drink hydrochloric acid, that doesn't happen very often, but I have seen patients drink muriatic acid. It was a suicide attempt. She was trying to end her life, and she drank muriatic acid, and really caused a lot of problems in her esophagus and her stomach, and they had to go in and surgically repair that. But under the circumstances, with this acid added to the system, her body used the sodium bicarbonate carbonic acid buffer system to minimize the effects that acid had on her pH, because enzymes and the breakdown of tissue happens optimally at a pH that's fairly narrow. So if we take this strong acid, HCl, and we add the buffer system, there are also other buffer systems. There's the blood buffer system, there's the phosphate buffer system, but the one that we pay attention to, the one we make sense of, is the sodium bicarbonate carbonic acid buffer system. So usually what we'll do is we'll tear apart these. As you know, hydrochloric acid then donates its hydrogen ions. So we've got a hydrogen ion here, and we've got chloride. And so what we do is we take this weak buffer, and we combine the hydrogen with another hydrogen and a bicarbonate, plus chloride and hydrogen again. Okay, well, let's see. Do this. Sodium. Na plus, is that something else? So if we recombine sodium bicarbonate with this strong acid, we end up with a weak acid and salt, basically, NaCl. So salt plus the weak acid would minimize the effect of that strong acid on the pH system. So the buffer system recombines these compounds to make minimal changes in the pH. Instead of going from a 7.4 to a 7.0, maybe by recombining it to carbonic acid, we would only have a 7.25 pH change. Okay, so we change with the buffer system. We change the strong acid to a weak acid and salt. Okay, we also do that with bases, and one of the most important strong bases is NaOH. It's sodium hydroxide, and the text uses this just as an example of how we minimize changes to the pH if we have strong bases as well. So sodium hydroxide is recombined with the sodium bicarbonate carbonic acid buffer system, and it dissociates into its parts, sodium and hydroxide, and the OH on the hydroxide. But we're going to combine it. If this is a base, we're going to combine it with this acid. So we get NaHCO3, and here we get another H. So in this case, this is a strong base. In this case, this is a strong acid. And what the buffer system does is it changes the strong acid to a weak acid. And in this case, it changes the strong base to sodium bicarbonate. Okay, sodium bicarbonate plus, what's OH plus another hydrogen? There's two H's there.
H2O.
And an O. So it changes it into bicarbonate and water. So it's just, the text uses that as just an example to show you how this buffer system is recombined with a strong acid and a strong base to create a weak acid and a weak base. Okay, so it would minimize the effect of changes on the pH. Okay. So the buffer system is in play to help to minimize changes on the pH. Well, in acid-base balance, then, if we're concerned about how many hydrogen ions there are, the higher the PaCO2. So when we breathe, we're able to draw blood gas from the radial artery, the femoral artery, or in cardiac arrest states where patients' heart stops. CO2s always go up. And if CO2 goes up, let me use this example. So if CO2 goes up, that's as a result of hypoventilation, right? Carbon dioxide is a direct byproduct of ventilation. So if we're hyperventilating, CO2 goes down. If we hypoventilate, CO2 goes up. And that influences pH. So if CO2 goes up, then carbonic acid has to go up, hydrogen ions have to go up, and bicarbonate has to go up. So we keep these things in molar concentrations. Okay? The human body is taking these chemicals and they're trying to equate them, they're trying to balance them out ionically, and they keep them all in molar concentrations. But when physiologic processes like ventilatory failure, so in ventilatory failure, have we defined that yet in any class? Ventilatory failure is equal to a P little a CO2 of greater than 60 millimeters of mercury. So you've already said that CO2 is normal 35 to 45, right? We've all recognized that. As long as CO2 is within 35 to 45, that's considered to be normal, and 40 is right in the middle. But if the CO2 ever rises above 60 millimeters of mercury, that's technically ventilatory failure. For whatever reason, the lungs aren't working and CO2 is rising. What would you expect to happen to the pH? If the CO2 is rising, then the pH is falling and the patient gets an acidosis because of it. So acidosis is an assessment, and when we draw blood gas, we're looking at acid-base balance. So when we get an acid-base number or a measurement, then it's telling us if the patient's acidotic. And many of those patients that are acidotic because the respiratory system is deficient, it's failed, and so the CO2 has risen above 60. Does that make sense? So we call respiratory failure a PaCO2 greater than 60 millimeters of mercury. And when it's above 60, the CO2 is high, the pH becomes acidic. And we can treat that. How do we treat a respiratory acidosis? Yes, thank you so much. That's very good. Yeah, it's as simple as that. We ventilate. We put a tube into their lungs and we make them breathe, or we put a CPAP or BiPAP over their face and we make them breathe. So we remove CO2 that brings their pH back to within normal limits. Very good. I mean, it's so simple. It's got to be harder than that, right? And it's not necessarily that hard. So, yeah, you ventilate. So we treat respiratory acidosis through ventilation. And we keep patients' pHs within fairly small ranges, 735 to 745, by ventilating. So respiratory failure is a high CO2 brought on by respiratory failure. And all the disease pathologies you've been talking about so far, bronchitis, bronchiectasis, pneumonia, asthma, all of these pulmonary problems can lead to respiratory failure. And so our role is to simply help them to ventilate. Yeah, we want to change PaCO2. Okay, so we can minimize the effect of strong acids and strong bases by a sodium bicarbonate carbonic acid buffer system. It improves or minimizes the pH level. Well, pH is the inverse log of the hydrogen ion concentration, but we can also measure pH is equal to the pK plus the log base 10 of bicarbonate divided by carbonic acid relationship. So bicarbonate and carbonic acid, that's this one and this one. The relationship of those two things is relative to CO2, but this particular equation is called Henderson-Hesselbach. This is going to be important for us. Henderson-Hesselbach. And Henderson-Hesselbach then describes how we make sense of pH. We can generally describe it as the inverse log of the hydrogen ion concentration. So pK is always 6.1. Okay, that'll always be the same. pK is not going to change. That's an association constant. And the log base 10 of bicarbonate, well, we can measure the bicarbonate, and it's usually on an ABG, and it's the normal level is 22 milliequivalents to 26 milliequivalents. Okay. So usually the amount of bicarbonate is between 22 and 26. Well, what's right in the middle of 22 to 26? 24. So we're going to use that as the normal. Okay, 24 milliequivalents. So if the pH is equal to the pK plus the log base 10 of bicarbonate to carbonic acid, well, an ABG suggests that 24 milliequivalents is the normal level for bicarbonate. And how do we find the amount of carbonic acid? It's consistent with the amount of CO2, because here you've taken CO2 and water and created carbonic acid. And go back to that diagram, Alicia, on 295, in that little box at the bottom. What does it say CO2 is equal to, or the bicarbonic acid is equal to?
All levels in plasma?
Yeah. PaCO2 times what?
0.03.
0.0301. So carbonic acid, H2CO3, equals the CO2 times 0.0301. Well, on that same ABG, we know what the CO2 level is, and so what's normal CO2 on the ABG? 35 to 45 millimeters of mercury. So right in the middle of that is 40 millimeters of mercury. So if we suggest that the PaCO2 is 40 times 0.0301, that equals 1.2. So I've just set up a relationship looking at pH as the amount of bicarbonate divided by the amount of carbonic acid. It's the relationship of hydrogen ions, right? Bicarbonate to carbonic acid. So 24 divided by 1.2 is what?
20.
20 to 1. That's really interesting. And that becomes extraordinarily important.
Carbon dioxide to bicarb.
This is your bonus for the third exam. This is the reason for being here today. I'm going to give you this. That tip. 20 parts to 1. That's really, really important. The way that we maintain normal pH is by maintaining a relationship of the amount of bicarbonate to the amount of carbonic acid. And what this means, what the 20 to 1 means is that bicarbonate we keep in 20 parts. 20 parts of bicarbonate to every 1 part of carbonic acid. What does that mean in terms of the relationship of ventilation and breathing? Because there's a relationship of CO2 to ventilation, right? The less we breathe, the higher the CO2. And so the higher the CO2, the higher this number gets. So which one of these two factors, bicarbonate being composed in the pH of 20 parts, or carbonic acid being composed in the pH of only 1 part, which one of those has the most profound effect on pH? Bicarbonate or carbonic acid?
Carbonic acid.
We need 20 parts of bicarb, but only, so if we raise, and you're right, Kyle, if we raise the carbonic acid 1 part, how many times do we have to raise the bicarbonate by to maintain equilibrium? 20 parts. So if this goes up by 1, this has to go up by 40. So the biggest influence of pH is carbonic acid, and by virtue of the relationship, CO2. So CO2 is really an important piece, although the way we've been making sense of it so far is all in terms of ventilation. We can change ventilation very quickly by hyperventilating and hypoventilating. But what the pH is doing, the pH is recognizing a relationship between carbonic acid and bicarbonate, maintaining a 20 to 1 relationship. The most important piece is the relationship of bicarbonate to carbonic acid. Carbonic acid having the most influence, having the biggest influence on pH. So, if that so does anybody have a log function on your phone?
What?
So if you put in 20, the number 20, because 20 over 1 is 20. 20 parts of bicarbonate for every 1 part of carbonic acid. So just put in 20 and push the log. What do you get? Should be 1.3.
Yeah, 1.3.
So when we describe pH in terms of Henderson-Hasselbalch, it's the pK plus the log base 10 of the relationship of bicarbonate to carbonic acid, which numerically should be 20 parts to 1 part. So the log of 20 is 1.3. 6.1 plus 1.3 is 7.4. There's where pH comes from. The log of 20. As long as the relationship is 20 parts to 1, then our pH should be 7.40. What's normal pH? 735 to 745. 7.40 is right in the middle. So as long as the relationship of bicarbonate to carbonic acid is 20 parts to 1, the log of 20 is 1.3 plus the pK of 6.1 is 7.4. That 7.4 is where we get normal pH. Okay. We better take a break there.